Hello, everybody. My name is Patrick Smith, and this is my partner, Tyler Gonzalez, and we are today representing General Dynamics Electric Boat with our project, the Digital Twin. The first question a lot of you may have is, what is a digital twin? A digital twin is essentially a virtual replica of a physical component or system that's capable of system monitoring and system control, but the key aspect that we're interested in is predictive maintenance. For those of you who don't know, Electric Boat produces nuclear-powered submarines for the Navy. So being able to perform predictive maintenance on any of its numerous components inside the submarines is very valuable. Submarines already spend a very large portion of their lifespan in docks getting maintenance performed on them. So being able to predict when maintenance needs to be performed and when it doesn't need to be performed can help save the company money and time. It can increase the performance of the pumps or of the systems, increase their lifespan, and reduce maintenance costs overall. But the world of digital twins extends far beyond exclusively submarines. Digital twin can be applied to virtually any physical system or component and be exclusively beneficial for whatever it's attached to. Any component can benefit from having reduced maintenance times as well as reduced costs. In the world of nuclear submarines, there's also an additional aspect that digital twin offers, which is safety. Imagine you're on a nuclear submarine and a component starts to fail. That can be very dangerous for everyone who's on board. But with predictive maintenance, we can predict when that component is going to fail and catch it before it does, thereby helping increase the safety of the sailors on board. Our project specifically consists of four main components: the embedded hardware, this one doesn't have a laser pointer, the embedded hardware, the modern software architecture, the real-time interactions, and the machine learning aspects. So moving on to the embedded hardware, the first thing we have to discuss is the design as well as the component safety and the hardware degradation. The main design for our project was a pump with embedded system of sensors attached to it. The first thing we had to do was select what we were going to use as our foundation. We chose the Bosworth pump that you can see up there, and we selected a series of sensors to attach to it. We decided to go with four main points of data to collect from it, which is the output water flow from the pump, the electrical current being drawn by the pump, the speed the pump is spinning at, and the ambient sound of the pump itself. We had to select all these components and the pump and everything from scratch, since it was a very open-ended project to begin with. That was a fairly difficult task for us because we had to make sure everything was going to work together. We selected an Arduino microcontroller to take everything together and feed it to the laptop that we used to do all of our calculations on. We also created a water loop up there, which is just a simple box water tank with some hoses going into and out of the pump. That way we can run the pump for an indefinite amount of time and collect as much data as we need on it without having to stop. Safety is a concern with any project. Ours is no different. Obviously, we were pumping water through our pump, and water and electrolytics don't mix very well. So that was our primary concern with safety. We wanted to be sure that the water wasn't going to get any of the electronics wet, so we made sure everything was enclosed within that watertight box up there. We also installed drains into the tray that the pump is situated on so that water won't flood up. We also had to install some sensors near the moving components under that blue cover, so we had to be extra careful that they weren't going to impact with any of the moving parts and break anything or cause any physical harm to us. The last aspect of the hardware we have to discuss is the simulated aging. In order for the algorithms to understand what a damaged pump looks like, we need to feed it data of what a damaged pump is, so that way it can be accurate with its predictions. Since the pump we chose was very durable, we found that the best way to damage it was through the diaphragms it uses to pump the water. We ordered several replacement diaphragms, and we actually found that the best way to damage them was with acetone, which reacts very negatively with the nitrile rubber diaphragms that we have installed. We tried a few other methods. We tried boiling them. We tried stressing them in ways that they're not meant to be stressed, but we found that the acetone is the best way to get a good consistent damage across all of the diaphragms. We ended up having several different diaphragms damaged at 30-minute intervals, intervals of time being submerged inside the acetone up to 2.5 hours, which is a great baseline for us to gather all of our data. Now I'm going to pass it on to Tyler to discuss the software side.
So for the software, we had three major software components: the embedded microcontroller, which handles all of the data processing from the sensors; the backend system, which does all of the data analytics and machine learning predictions; and the MATLAB front end, which handles all of the user interactions. The embedded system does all of the data processing to create the most optimized performance overall inside the system. It takes all of the raw sensor data and performs complex signal analysis to extract the actual values and sends all of that to the MATLAB backend in USB via real time. The back-end system takes all of this data and performs data analysis and combines that with data taken from a time series database that was developed and creates a extremely complex machine learning algorithm using bagged regression decision trees and predicts the lifespan of the pump and displays that to the GUI. And as you can see here, this is a prediction tree using the machine learning algorithm. It was able to map predictions of the lifespan along that curve using the data that Patrick provided. Now here is the graphical user interface that was created. On the top half of this interface, you're able to see the machine learning predictions numerically and graphically. On the bottom half, you're able to see all of the real-time sensor data, and you're even able to refresh the sensor values and sensor averages to get a better understanding of the system. And you can see just how accurate the machine learning predictions are on the top of the screen. You're also able to see all of the real-time sensor data in a tabular format by connecting to the database. You're able to specify which data you want to look at. And you're even able to view the data graphically by connecting to a graphical user interface here. And you're able to change how much data you're able to see on the graph specified by the user. Now, based on all of our software testing, we were able to confirm that our best anticipated outcome was achieved. We were able to build a functional framework for digital twin prototype using consistent and reliable predictions from the machine learning algorithms. And we were able to do all of this with minimal investment into the software architecture and sensor architecture. And with that being said, we would like to thank everyone who made our project possible.